Hello everyone and welcome to Computational Methods Homework 4. Today we're going to be implementing the NRTL activity coefficient model in Python. And we're going to compare three different ways of calculating these activity coefficients. And we're going to test them all three on equal molar mixture of methanol, ethanol, and water. Okay, so let's get started. So what is the NRTL model? Well, it starts with Raoult's law. And Raoult's law is a relation between the vapor pressure of a component and its mole fraction of liquid in its mixture. So mathematically what it's saying is the partial pressure of the component in a gaseous mixture above a solution of liquid or of solid is equal to its equilibrium vapor pressure of the pure component and the mole fraction of the component I in the liquid or solid solution. So if we have more than one components in mixture, let's say a mixture of ethanol and water, then the vapor phase above consists of both ethanol and water. And once they reach equilibrium, the total vapor pressure of the solution is the sum of all of these components of their partial pressure at it's equal to the vapor pressure multiplied by their mole fractions overall. And we can also say that as the mole-weighted mean of the individual vapor pressures. Okay? So, but where do the activity coefficients come in? Well, when you're doing this when you're operating these equations using real components, they sometimes deviate from the expected and like the estimated. So what you do is use activity coefficient signified by this Greek letter right here. And what that does is that multiplies the p star and the x by a specific coefficient. It's usually around 1 to account for like minor corrections. But those minor corrections can have a big impact if you have when the solution is kind of equimolar, and we'll see that as we go. So how do we find this activity coefficient? Well, today we're going to be using the NRTL model, or the non-random two-liquid model. And what it does is it correlates the activity coefficients with the mole fractions in the liquid phase. So as you can see, this is an example of what of the NRTL model in action. So we have these two extrapolated lines here, the blue and the red, at different pressures. And then we have this green one, which is a fitted line for all this experimental data. And the NRTL model can calculate all three. And as you can see, this data here, which was captured at 101 kPa, falls right between the 10 kPa and the 1000 kPa. And we're going to be using this model as we go forwards. So what is the model? So these are the equations for the binary mixture, where we have the natural log of So we can see here the basis of the NRTL model for a binary mixture, where we have the natural log of this gamma, which this gamma is the activity coefficient that we're trying to solve for. And you can see there's one for each component in the mixture. And that equals this x, this molar fraction of the other component, multiplied by these two terms that we're going to calculate. Now, this is just for a binary mixture. Well, what if we had 3 components in mixture? Well, here are the general equations, where we have our. So let's kind of break this equation down. So we have this Gij, which is equal to the exponent, or this negative alpha times this tau, all raised to the power of e. Alpha is equal to this correlation, which is based on temperature, and tau is also based on temperature, and you can see the temperature terms in this equation. And as you'll notice, there are actually several different equation forms for alpha and tau. And these are just the general ones. The one we're going to use for tau, actually, we have these b constants, but since we're not going to use any others, so our tau equation is just going to be this tau ij equals bij over t. And I, as a reminder, I is the species, or is the species we're looking at. So what we're going to do this is each component has one activity coefficient. So if we have component 1, we'll have gamma 1. And component 2 will be gamma 2. Well, you notice how some of these have a J also. Well, the J is going to be the component that it's interacting with. So in a 3 component mixture, there'll be interactions between component 1 and component 2, and component 1 and component 3, and so on and so forth for the other 2. So there'll be several that we'll have to look at. A total of 6 different interactions for this G, alpha, and tau values. Okay. So let's use this snip to grab a picture of this. Okay. So paste it. Oh, excuse me. Okay. So here's our equation. Actually, let's add a header, and we'll call this just NRTL activity coefficient model. Okay. So these are the equations we're going to need. And so the first thing what we're going to do is our professors provided us with some data that we'll be able to use for this. So let's extract that data now. It's -w. So in order to access databases in Python, the way we're going to have to do it is wget -n-q. Then here's the data here. So let's copy and paste this URL. -o. And we need the che4.ipynb. Okay. Then the next thing we're going to need is pip install import NB. Run that, let's make sure it connects, because we need it to be able to connect to this database and read it. Okay, while it's connecting there, let's import numpy as np. And we'll import, okay, so we got that. All right, so now to the actual equation. So because of these summations here, and the fact that we have a 3-component mixture, what we're actually going to have to do is we're going to have to use some sort of summation technique to calculate these activity coefficients. Now, in our problem description, it wants us to use Python loops, einsum, and matrix vector multiplications. So we're actually going to implement this model 3 times using 3 separate way of doing it, and then we're going to compare them. So I want an equimolar mixture of methanol, ethanol, and water. Let's actually define those variables first. So first thing we're going to need is we're going to call in our components. So we need methanol, ethanol, and water. So we're going to use props, which is a Python class, methanol, ethanol, water. Oops. Okay, then we're going to give it its component molar fractions, which it wants it to be equimolar. So we're going to give it 1/3, 1/3, and 1/3. Okay, and then we're going to set t equal to 300, because we want that at 300. Okay, so we forgot to import our props. So what we need to do is from import NB, we need to import notebook. And then we need to and we'll also import 2 other things that we'll need. We'll need x to q and q to x. Okay. Maybe it's let's run that. Okay. So now when you run this, it should work. Ah, yes. We forgot the brackets. Throw brackets on. Should be happy with that. Okay, so now we have those. Let's define our NRTL model. So let's call it NRTL loops. And what we need to give it is we need to give it x and t. Okay. So first thing we're going to need to do is we're going to need to give it values for tau and g. So let's start with tau. So tau is equal to this b here. So we'll just call it B, divided by RT. And the B comes from it comes from this. So it comes from P, the props, NRTL underscore B. Okay, so now we have that. Then we need to do, now for G, we want to set that equal to NP dot EXP, because we're raising this to the, we're calculating the exponent of this alpha. So we need NRTL, excuse me, P dot NRTL alpha. Yep, there it is. Excuse me, let's throw the negative sign in there. Negative. And then this is going to be divided or multiplied by tau. So times tau. Okay. So now that we have that, now that we have our G and our tau, keep in mind this will be it will calculate it as an array based on all of our based on the props we gave it. Now what we're going to do is we're actually going to look at these terms here. So you'll notice this term here, and this term here are all, wait, no, sorry. So actually, we can actually look at this further, that this whole term here is equivalent to this one. So let's call that x tau g div xg. Okay, so this is a variable representing this entire guy here. And we're initially going to set it, we're initially going to make an array, just an empty one of size okay, so now we have this. Let's also make one for the second term here. So let's just call it term 2. Because xg div xg would probably be pretty confusing after running this after looking at this a couple times. And we'll do the same. Just give it an array of zeros. Okay. Then we're going to need n, which is n is just, we're going to make this the total number of components, so just the size of our x. And then we're going to jump into our for loop. So for I in range n. So this first for loop, we're going to have 2. We're going to have 2. But the first for loop is going to be about this first term. So let's make another variable. It's called x tau g for this top piece. And we're going to set it for 0 initially. But then we're going to do a nested for loop. So let's call it j this time. Range n. Actually, let's make the zeros like x. That might work a little easier and be more adaptable to how big x actually becomes. And it's fine the way it is. So we went for this. Is we're going to actually calculate our x tau g. So the way we're going to do this is we're actually going to use a handy operator I learned about recently, which is this plus equals. And what we're going to need is x for j times tau for in the so remember tau and g, as we defined before, are matrices. And by doing it this way, we're actually going to be calling based off of these two guys here. We're going to be adding these values to here, making this an array also. So x times tau times g, and g will have the same ji index. Why are you? Oh, that should be lowercase. All right. So now we have this. So this is our top piece. Now then next we need the bottom piece, which is xg, which we honestly should probably define up here. So let's just call this xg equals mp zeros like x. So xg is going to equal our, it's going to look pretty similar. It's going to be xj times g at index ji. Okay, so that'll calculate our x tau g and our xg here, these two guys. Then we need a second for loop, just set it be set very similarly. And this one's going to calculate that second term. So this will calculate the second piece. Actually, before we're going to do that, let's do x tau g div g before I forget. We should actually probably give this guy his own index. And x tau g div g is just, x tau g divided by xg at index I. Okay. So now that we're in here, we're going to calculate our term 2, which we made as a 0 up here. Term 2 is just going to be xg. So yeah. No, sorry. It's going to be x from g to I. So we'll do j times g j comma I divided by xg. Let's actually fix this. That should be an I. We need the same operator from before. I think this one's a j. Then I have to add this last piece. So this is multiplied by tau ij, which is times this piece, which is the same as this. So it's going to be x tau g div g So now that we have all of that, we're going to return. Well, we want these. So we're going to return all of this. So np.exp. Then we have x tau g, get it right, x tau g div g plus this term 2. So x tau g div g plus term 2. Did I spell it wrong? Div xg. Thanks for catching that, Python. Okay, so we're clear of syntax errors. So now let's run this thing with just this, with just using these loops. So the way we're going to want to do this is we're going to do NRTL loops. We're going to give it x, we're going to give it t. If I could spell right, ladies and gentlemen, this would be a little bit easier. Okay, so we got activity coefficients. However, this one is kind of suspect. Remember how I said earlier that they're usually around 1? Well, most activity coefficients for normal temperatures, aka temperatures between like 200 and 400 Kelvin, are usually between 0.8 and 1.3 or so, because they're designed to be only like minor corrections to Raoult's law. So having a coefficient of 2.6 right here tells us that we did something wrong. So the first suspect that I'm thinking is that we got our indices wrong in this. So it might be this one right here, because looking at this, so it refers to this one here. And what we actually might want to do is this might actually want to be flipped. So this is I, and this one's J. So let's give that a shot. Run this again, run this again. Okay, so we're still at 1.6, which is still a little high. At least it seems high. Now so this is for water. And as we know from, so let's look back at Raoult's law. So having this activity coefficient here, what this refers to is, well, let's go back to the initial equation. Let's go back to this one. So normally what this would do is this activity coefficient would kind of go here, right? It'd go with the equilibrium vapor pressure and the liquid component fraction, molar fraction. Go there. So what does that mean as an activity coefficient? It means if it's greater than 1, then we'll see a higher partial pressure than what this equation would calculate alone. So lower than 1, we'd see lower. Well, water is, in this case, that actually might be correct. That's at 1.6. Because water is different from methanol and ethanol. Ethanol and methanol have similar properties, so we'd expect them to have similar, and exactly we have 1 and about 1.1. Water is a bit different, so I guess it wouldn't be as surprising if water was a little bit different than the other two. So let's put a pin in this, and we're going to go try using the einsum method, which was the second method to calculate this, and we'll see if they're similar. Okay, so let's put a pin in this. Let's do define NRTL einsum, and we'll ask for the same x and t. So for this, we can copy these first two terms, because we're going to need them, and that won't change. Okay, so next what we'll need is, well, we're going to want x tau g div xg, so just like before. And we're going to set that equal to, well, x tau g divided by xg. Okay, we'll use that in a second. Now what we want is we want to calculate what x tau g and xg equal. So x tau g is equal to einsum. So einsum asks, so excuse me, it's from NumPy. So the first thing that einsum needs is, first thing it needs the subscripts, so that's going to be j and I. And then it'll need the variable what we actually want to do. So with this, we want j and ji. So let's give it j, ji, and then we want it to go to I. So I think that's how that works. Then we're going to give it the operands, which are x, and then we want it to be tau and g. So tau times g. And since we've already defined tau and g here, we can just have them as a multiplication. Now we're going to do the exact same thing with xg. So np dot einsum. And this will be j, just double check, j to ji, yeah. And we need x and we need g, okay? So if you'll notice, einsum basically takes this whole loop, this whole nested loop structure actually, and kind of condenses it into two lines. Then we have this x tau div g, which is simply the, now that we have this x tau g div g, we have that right there. So now we're going to do the exact same thing with term 2. So, okay, so to do the second term, which we'll just call term 2 like before, it's going to be a little bit different. So we're still going to use einsum. And this time we want it to go j, ij. Send it to I. Then we want, so term 2 is this guy. Go away. So term 2 is x tau times g. No, it's just xg. then we're going to need to multiply this by tau minus this guy. So x tau g which these have different integrands, so what we're actually going to need is we're going to need to do it none and I divided by xg, which is none and I. Okay. Shoot, it kind of not supposed to be there. So we have x, so we're summing x, and then so we have g times throw this right here, because you'll notice we got this exact same guy here. Not close. Why is it telling me it's not closed? Looks like it's closed. Oh, excuse me, that's not right. Wrong programming language. I apologize. That should look like that. Then we're going to return this expression here. So we'll just copy and paste it. Okay, run that. Invalid syntax. Alright, so it doesn't like that. So what if we put that inside this? Okay, it doesn't like the next one. So let's put that inside the string and see if that works. Okay, so we're in. Alright, so moment of truth. NRTL einsum of x and t is an error. Okay. Fewer operands provided to Einstein sums and specify. Okay, so which line is it? It's one of these. It's one of the einsums. Okay, so we have our subscripts. We have j, we have ij, and then we have this indicator I. Then we have our operands. So we have x and we have g times this. Maybe it wants it all combined into one string, like so. Ooh, that is wrong one. Ooh, glad I caught that there. All right, so let's fix this up here. Run that, run that. All right, so it's still not happy with the arguments I'm giving einsum. So we have the operands, we have what it's doing, and we have what it's changing. Oh, she would tell me which one is the problem. Oh, I forgot the third one. Alrighty, so we ran einsum, and it actually gave us the same array of activity coefficients as loops. Well, there you have it. So that must be the right way of doing it. Okay, so now that we have einsum, we have NRTL, or then we have the Python loops method. The third method is to use matrix vector multiplications. Okay, so let's do that. So let's define that as NRTL matvac. Give it x and t. Okay, this one, let's copy these over. And we'll also want this guy, but later. Now for x tau g, we'll just straight up use matrix multiplication, which is that at sign. Then we'll want tau times g. X tau g equals that. Then we have xg equals x at g. Leave that one. Then let's go ahead and calculate term 2. So term 2 is this guy. So it's going to be x times g. So these are parentheses. X times g so x times g times tau minus this guy. So it's actually going to look very similar to this up here. It's going to be tau minus x tau g div xg. Let's do the same. Okay, close that. Divided by xg, none, comma, all. Close that. Okay, so that's our term 2. So we have our term 1 and our term 2. Term 1, term 2. What we need to do with this term 2 now, excuse me, this x, actually, let's call this A, is x times matrix multiplied of term 2. Okay, run that. Then we're going to return let's just copy and paste this from earlier. So we'll have to change this to A. Let's run that. Then we will NRTL matvac x comma t. Not callable. Okay, so we're getting this not callable array. So I'm wondering if the issue is this. And let's try getting rid of this and just doing natural log of gamma. Let me back. Now equals x tau g div xg plus x times this term 2. Okay, that makes a difference. So unfortunately, it's not telling me which one is uncallable. But I have a hunch that it might be the fact that these x's are not the right shape. So x, as a reminder, x is an array, a 1 by 3 array of 0.33. All three values are 0.33. So let's do it this way. Let's do rid of this. Okay. So I just ran these 3 lines as is with x and t already given, and it ran just fine. So let's keep moving. That's fair. Let's get rid of all these indents. So far, it's not having an issue. So let's do this one. Okay, so it is this line that is the problem. So this is an array with shape 3. It's an array with shape 3, so it should be able to add. That's an array with so 3, 3, 3, 3. That's a 3, 0? Or just a 3, 1 maybe? Three, 1. So it's a 3, 3, 3, 1 gives you a 3, 1. That makes sense. So you have a 3, 3 here, 3, 3 here. Those are adding together just fine. Then we have a 3, 1, which should divide into it okay. Then this G. What is G? G is an array, a 3, 3 array. So do I need a matrix multiplier there? So let's try that. Okay, so it gave us something. It gave us in a 3 by 3 array instead of a 1 by 3 array like we were hoping for. And plus, I don't see any of the right answers in this array, so that tells me that we might be doing something wrong here. So my hunch is that we're using the wrong x values in the wrong places. So let's actually reshape our x. So x equals p dot reshape. Let's give it, let's make this, instead of a 1 by 3, let's make it a 3 by 1. So let's try that. Run that. Oops. X comma. I don't think that changed our answer at all. It just might have flip-flopped it. Let's make these commas. Let's try flattening this answer. Oh, flatten has commas there. Then we want, actually, are these in the wrong spot? EXP. Are these in the wrong spot? These might be in the wrong spot. Hold on, let me fix this. No, I think those are in the right spot. It worked. But we want it to be a similar to these answers with only 1 row and 3 columns. So what if we squeeze this? That didn't appear to make a difference. So maybe squeezing it isn't the right answer. All right, well, the only thing I can think of is I'm doing this reshape wrong. That's odd. It works down here, but not up there. comment this out. What if I don't multiply this, and this is instead just a generic multiplication? Does that work? Cute. So it's upset because this is a 1. Why are you a 1, 3, 3? Why are you a 3-dimensional? Alright, so you're 3, 3. You're 3, 3. You're 3, 3. You're 3, 1. So let's see what this looks like. So we have the 3 3s minus 3 3s. No problem there. That'll work just fine. Then the next operation is to multiply a 3 3 by a 3 3, which should create a 3 3. And when you divide a 3 3 by a 3 1, then you should get not that. So that should multiply fine. Then we're left here. So why are we getting a 1 3 3 array? And maybe the answer is that we have to do this squeeze function. But that still doesn't help the fact that this isn't a 1 3 3 array. 3 3. Now become a 1. Let's run that. And yeah. So this is a 3 3, and we want these to presumably also be a 3 3. Okay, so I applied a squeeze, I applied a flatten. And we're still getting this 9-element array, which has now been flattened since I asked it to. But what we want is 3, so we're actually getting a 3 by 3 here. Yeah, 3 by 3 here. And what we want that to be is we want that to be a 3 by 1 or 1 by 3. So the issue, this should be a 1 by 3, I think. So let's throw parentheses around here. See if that's the problem. Voila. So as you can see by these three that are so much so everyone can see. As you can see by these 3 arrays, as a reminder, are the activity coefficients for methanol, ethanol, and water. And as you can see, all 3 of these methods produce the exact same result. So it just goes to show that pulling the data from this from my professor's GitHub, that you could use any of these 3 methods, the Python loops, the einsum, or the matrix vector multiplication, to get the activity coefficients for whatever components you want at whatever temperature you want. So join me in the following video, part 2, where we talk about calculating dew and bubble temperatures using that NRTL activity coefficient model. So, I'll see you there.